Thank you all. There we go. So thank you all for coming back from the poster session. I hope you were able to join it. My name is Emily Ryan. I'm one of the organizers for the symposium and in the mechanical engineering and materials science and engineering departments at Boston University. And so we're going to move into session 2, machine learning innovation in support of chemistry and materials science. And I'm going to introduce you to Konstantinos Spilopoulos. And I hope I didn't butcher your name too bad, Kostos. He's an associate professor in the Department of Mathematics and Statistics at Boston University. He's also affiliated with the Division of Systems Engineering, and he works on computational and algorithmic methods in machine learning, statistical learning theory, network analysis, Monte Carlo simulation methods, and stochastic modeling. And he will be our introducing everybody today for this session. So I'll give it to you, Kostos.
Okay, Emily, thank you very much. So my role here is to basically make sure that everything is on time and on introducing the speakers. So the session is titled Machine Learning in Support of Chemistry and Material Science. And our guests today have used techniques and algorithms in many applications in chemistry and material science. And have all worked on fundamental learning tools associated to such structured data. Now, I want to say that the organization of this session took a number of people that we had to brainstorm. So I would like to thank Brian Coolidge, who is an associate professor at electrical and computer engineering at BU, and who will also be the moderator later on for the discussion. And Eric Kolachi, who is the director of the Hariri Institute, and Yves Atzade, who is also a professor in maths and statistics. Now, before we go on, I need to remind that this is being recorded and that will be posted to the Hariri's Institute YouTube channel at some point this week. Please ask questions, but please use the Q&A. And they will be essentially discussed in the panel discussion that will follow the 3 presentations. Now, for the presenters, we'll start with Professor Frank Noy, who may not remember me, but we met at a conference a few years back in Germany. Briefly, who is a professor in the Mathematics and Computer Science Department at Freie University in Berlin. Rishi Kondor, who is an associate professor at the Computer Science and Statistics Department at Chicago, and Bidisa Samantha from Google. So let's start with Frank Noy. Please, you have the floor.
Thank you, Kostas. Thank you very much for the nice introduction. And so I'll share my screen. Here we go. I hope you can see everything all right. You see my mouse, right?
Yes, yes.
Cool. All right, so I will give you an overview of deep learning for the molecular sciences, which is mainly what we're doing in the group. And so this is, my group is called actually AI for Sciences. And basic idea here is that if we design an AI system or machine learning system, then we have to keep certain things in mind and solve certain problems. So here are some some well-known examples of machine learning and AI. This is robotics, and this is reinforcement learning for playing games. And when we develop machine learning algorithms or AI systems, basically we have to answer 2 questions. What is the optimization problem? So what are we optimizing? Because generally ML problems are formulated as optimization problems. And what is the structure or the architecture of the machine learning algorithm which holds the parameters? And if we are solving problems for physics, or molecular physics for that matter, then physics has a lot to say about these choices. So for example, there may be a fundamental physical principle, such as a variational principle also, which defines the optimization problem. So very often we're not just in the situation that we have inputs and labels given, and we just want to minimize a prediction error on those, but we often have some fundamental physical statement about what is it actually that we want to optimize to solve a given problem. And secondly, we have a similar situation with the parameters in the model architecture. So often in physics problems, we have certain aspects that we want to satisfy. For example, we may have certain symmetries in a solution, like the energy of a molecule may be invariant to translating or rotating that molecule. And maybe that's something we want to enforce in the machine learning predictor as well. So physics often tells us what kind of aspects do we want, what kind of properties do we want to have in the machine learning architecture, and can give us a lot of guidance in developing it. And so here I will just give a spotlight on two of the things we've been working on. So one is the sampling problem, the other the electronic structure problem. And just to give you a brief introduction to the sampling problem. So here you see a molecular system. These are two proteins, and actually very small proteins. And they are embedded in a solvent box, so basically a box of water molecules. And the system has about 100,000 atoms. And we can simulate that with all atom molecular dynamics simulations, where we basically compute energies and forces between all of the atoms in every time step. And then we make tiny time steps on the order of 1 femtosecond. And we just propagate that. We just simulate the system forward in time. And we can do that by running, for example, MD simulations on a GPU. And about 1 week of real time will give us about 1 microsecond of simulation in this system. But these two proteins can bind to one another. And actually one is an inhibitor for the other protein. So they can kind of bind very tightly and then stick together. And so just simulating that binding process is something that will take about 50 microseconds in reality. So simulating that will take us about GPU a year. But simulating this dissociation would take us 1 million GPU a year. So that's really not a straightforward way to do things. And of course, there are a lot of enhanced sampling methods and a lot of tricks to overcome this problem, because this sampling problem is an old and well-known problem in molecular simulation and in statistical mechanics. And one approach we can do, for example, is indicated here. So this is using a so-called Markov state model. So the idea there is basically we started simulations in different places of conformation space, so like in dissociated states, associated states, kind of intermediates, etc. And we just did relatively short simulations because we just used them to collect conditional statistics. Like if we start in this state, with what probability does it go to that state? So we kind of build a map of this high-dimensional conformation space. And there are a lot of tricks behind the scenes, like how do we discretize these high-dimensional spaces well so that we actually distinguish relevant changes and not just noise. But without going into details here, basically this is something you can do, and you can collect data which just generates kind of a Markov chain. So like a summary statistics model of this binding unbinding process of these two proteins by running a net amount of 2 milliseconds worth of data. And this is something that's actually feasible on a compute cluster in many parallel simulations. Right, still, this is an expensive simulation. So 20,000 GPU days were needed to run that amount of data. And you can convert it into energy, and that's roughly 500 gigajoules. Or if you compare that to the combustion energy of Saturn V rocket, it would be about 1/3 of that. So it's still a significant computing effort to get that one simulation that tells you something about how this exact pair of two proteins bind and unbind at this exact set of conditions. And of course, it would be cool if we had a way to to do such calculations in a much more efficient and less time-consuming way. And an idea comes from generative deep learning, and that is leading to these Boltzmann generators that I will briefly allude to. And the idea here is the following. If we have the energy function of the molecular system, let's say of these two proteins, this energy defines, together with a statistical ensemble, such as the canonical ensemble at a certain temperature, defines the probability distribution of states that we would like to sample. It's just hard to do that, right? But in generative machine learning or generative deep learning, you have exactly this problem. So you actually want to generate samples from a very complicated distribution, such as you want to generate samples of faces of VIPs by, in this case, just learning from a database of such images about this distribution and then efficiently sampling from it. Right, so in this case, it's not even clear what this distribution is. What does it mean to be a sample in a data set of celebrities? But the idea, of course, is that you train a machine which is able to generate faces that kind of look like celebrities to you without you noticing that they're actually generated, they're not real people. And this is an example output of a model called GLOW, which is now actually a few years old. So this is kind of behind the state of the art, and you can really generate faces that look deceptively real in high resolution. Okay, and we use the same idea to generate molecular simulations. And what we use here is a so-called normalizing flow. Normalizing flow is a special type of neural network which is invertible. So for every input, we can generate an output, but we can also invert that output back to the input. So it's basically an invertible function, a bijective function, which is trainable. And because it's invertible, we can use the transformation of random variables rule for invertible transformations and compute the probability of generating a certain output, X, so a certain molecular configuration from the neural network, given that we know the probability of generating the input. And if the input comes from a simple distribution, like a Gaussian distribution, that is easy to do. And then we just have to be able to compute this determinant of the neural network. And with certain architectures, again, this is something we can do. And now we do a final step. Since we can compute the probability of the output, and we know the probability density that we want to sample from, apart from the prefactor, we can use reweighting, such as importance sampling or Markov chain Monte Carlo, in order to reweight this neural network sample to our exact output distribution. And we can use that to compute statistical mechanical properties, such as expectation values. And here's an example for that. So this is a small protein, PPTI, has about 1,000 atoms. Here's the secondary structure representation, and here's the all atom representation. And this is actually a sample that was generated by such a Boltzmann generator. So you actually take a 3,000 dimensional Gaussian distribution, take a sample from it, push it through the neural network, and you get basically all of these atoms here placed in one shot. And you can do this with different structures, and you can also show that you get reasonable statistics for like bond lengths, angle distributions, etc., etc. So this kind of may open up a way to generate efficiently various different molecular structures in situations where it would take a very long time for an MD simulation to travel from this structure to that structure here. And it's using deep learning to do that. And just to give you a second example, so here's an example from quantum mechanics, electronic structure calculation. So that's PauliNet. And in PauliNet, basically, we want to solve the electronic Schrödinger equation in using machine learning methods. And we want to do that. Here's the reference and the main protagonists of this work, Jan Hermann and Simon Schätzler. We want to do this because getting high accuracy solutions for quantum mechanics is important for many, many applications, such as for drug design, such as for material design, designing batteries, alloys, solar cells, etc. And basically what we really want to do here is we do not want just to make predictions from given solutions of the Schrödinger equation, which is the more commonly thing done in machine learning for quantum chemistry. We want to solve this equation. So really, we want to have a quantum chemistry method, which is using a neural network to represent the solution of this equation. Okay. So this equation consists of the Hamilton operator, which defines the molecular system. And it's an eigenvalue problem in this form. So there's the stationary Schrödinger equation. So we basically are looking for these functions, wave functions, which describe the electron distribution, and the eigenvalues, which are the energies of the quantum states. And typical problem is here, we can approximate the solution with different quantum chemistry methods, but the more accuracy we want, we want, the much more price we have to pay. We have to pay exponentially more higher for getting a little bit more accuracy. And there is an outlier here, which is density functional theory, which is quite accurate and quite cheap. And basically our method is proposing to be somewhere here, n to the 4, n to the 5, where n is the number of electrons, and is hopefully much, much more accurate. So hopefully another such outlier. And what's the machine learning problem here is it's a variational formulation of this eigenvalue problem. So we can formulate this eigenvalue problem variationally by searching for the minimum energy over a family of functions which are trying to approximate the true wave function. And we approximate the wave function with the neural net. And then this variational energy is our loss function. And so the main problem here is, and this is where the machine learning architecture comes in, is the structure of the solution. Because we are not just searching over any type of function, we are searching over antisymmetric functions. So what does that mean? It means the function, the wave function that we're looking for, should be such that if we take two electrons with the same spin and we exchange them, exchange their positions, then the sign of the wave function should flip. And a consequence of this is that this function should approximate 0 as two same spin electrons approach each other in space. So that means there should be 0 probability to find them here. And this is actually the Pauli exclusion principle. And hence this is called Pauli net. Okay, how do we do this? We harness a trick used in quantum chemistry as well. We use matrices, so-called Slater matrices, and use their determinants, because the determinant of a matrix is also antisymmetric with respect to exchanging the rows of the matrix. And so in standard quantum chemistry, this is used in the following way. We have n electrons. We have a basis set, so we have a set of functions that we use to build the wave function from, as a linear combinations of these functions are used to build the wave function. Okay, so then we just select n of these functions, we place the n electrons on them, and the pairwise combinations of electrons and wave functions basically gives us entries to such a matrix, and the determinant of this matrix, that is an antisymmetric function. So that has the right property. Sorry?
Ding.
That's a bing.
2 minutes.
Yes.
Okay, let me wrap up. So that gives you a valid solution, and sums of such determinants gives you a valid solution. Problem is a single determinant that gives you the Hartree-Fock solution is not very expressive. And if you want to get very accurate with a fixed basis set, then you need exponentially many determinants, because there are exponentially many ways to select n functions from a larger set of basis functions. And this is where deep learning comes into play. So instead of doing this, which is fun, this discrete exponentially scaling problem, which is fundamental problem where you cannot get the exponentially out of, we are actually using a deep neural network to transform the n electron positions as a function of all the other electron positions. And this trick is called backflow. So these resulting quasi-electron positions are now basically having multi-body information in them. And with that, we enter determinants, and only few determinants, that we can get much higher accuracies, because now we can learn effectively we can learn the orbitals. And with this approach, we can essentially get solutions to small quantum chemistry systems that are comparable to high accuracy variational quantum Monte Carlo solutions, but we can get that with about 2 orders of magnitude less matrix determinants. So that means hopefully much better scaling in the long run. Okay, and with this, I'm wrapping up. So why do we do deep learning? Not just because it's deep, but basically deep learning allows us, is basically kind of a programming language to express whatever we want to compute in a way that also automatically gives us a way to train any parameters in the process, because it constructs a differentiable graph. And in this way, we can do very complex operations, and we can build in all the components that we would like to have in the solutions or in the algorithm that we would like to run. And we can automatically differentiate through it and train a learning system. And that makes this so powerful. And with this, thank you for your attention. And thanks to my group and the funders. And yeah, happy to take your questions later in the discussion.
Frank, thank you very much for the presentation. We'll keep the questions for the panel discussion later on. So for those of you that have questions, please write them down and save them for later for the panel discussion that will follow after we conclude the presentations of this session. Now, our next speaker is Professor Issy Condor from Chicago. Frank, if you, and share, and thank you very much.
Okay, so let me start the screen sharing.
Yep.
All right, can you still see my slides?
Yes,
Good,
yes.
excellent. All right, okay.
Yours.
Thank you very much, and thank you for inviting me to this session. So I'd like to follow up Frank's talk. We're talking about some of the underlying principles that have emerged in this field of using machine learning, specifically deep learning, for learning the properties and states of physical and chemical systems. In particular, this notion of equivariance. So I'm going to give a brief overview of what equivariance is and how to account for it in neural networks. And then I'm going to talk about a specific case of this is permutation equivariance in graphs, which I'm excited about because it's kind of a newest work. The archive version has just been put up on the web. All right, so broadly speaking, the two types of problems that we've been looking at come either in the form of learning some properties or some physical quantities related to the positions of parts of a system, such as atoms, and learning force fields. So that's on the right. So learning the forces as a function of the molecular configuration. That's also kind of similar to what Frank talked about. The other type of problem is just learning things from the topological structure of the graphs of molecules. So that is essentially just the graph learning problem. So that is on the left. But these ideas of equivariance applied in both cases, because equivariance is really just the way to implement or enforce symmetries in learning algorithms. So in both cases, we have a natural symmetry group. So in the case of, say, force field learning, want to be symmetric with respect to the action of the rotation group, or more generally the Euclidean groups, the rotations and translations. Whereas in the case of graphs, we want to be symmetric with respect to the spurious transformation of just relabeling the nodes. Okay. So for the sake of just this presentation, I'm going to think of a neural network in the simplest possible way as kind of this convolutional type neural network, where all that we have is just the sequence of learnable linear transformations interspersed with pointwise nonlinearities. Okay, so this is our architecture. It can really be written down as just a function. As Frank said, ultimately neural networks are just a fancy way of writing down complicated functions and with some parameters and learning those parameters by stochastic gradient descent. Okay, so this is our architecture, and we want the whole thing to be invariant to the action of some symmetry group. So one way that we could do that is we could have every single layer be invariant, but that means that at every single layer, we would be losing a lot of information. So instead, the philosophy behind equivariant neural networks is to carry this group action kind of from the beginning to the very last layer and just make it invariant in the last layer. So if cats are very important for neural networks, that's well known in the field. So in terms of cats, this means that if you want to make the neural network invariant to rotations of cats, then all the intermediate layers, the representation that the neural network carries of this cat is going to rotate if you rotate the original cat. And at the very end, you have some invariance where you can just mod out by this rotation. So because you know how the intermediate layers transform, they do transform under the group, but in this very controlled way, you know how to mod out with it at the end. So basically, this is just the idea behind equivariance. And this is actually not new. So in general, in deep learning, one of the most successful, one of the biggest successes has been, of course, the application in vision. And the standard technology there is convolutional neural networks, which have been going since the 90s. And there are various ways of thinking about convolution. One way of thinking about it is just kind of some pattern matching idea. So that's fine. But really, every layer of a convolutional neural network implements this mathematical operation of convolution, which naturally satisfies this equivariance property that if the input to the layer is translated, then because you're just essentially doing this pattern matching, the output is going to be translated the same way. So this is why convolutional neural networks are equivariant to the action of the translation group. If you translate the input to the layer, then the output to the layer is also going to translate, no matter what potentially complicated stuff goes on inside the layer. So when it comes to learning physical systems, what we're interested in is generalizing this principle and the underlying mathematics to the action of other groups, in particular, things like the rotation group and the symmetry group. And one reason that's going to be more complicated, it's obvious from the start, is that these groups are not commutative, unlike the translation group. So the technology is going to have to be a little bit fancier. But fortunately, the underlying concepts do generalize very nicely. So I'm not sure if you can take in everything in this slide in this 50-minute talk, but maybe we can go back and look at it later. On the left are the classical notions of translation and convolution and equivariance, which is implied by them in the case of commutative groups, or in particular, just the Euclidean group. On the right-hand side, there's the corresponding notions in this more general group theoretic sense. So you see that each of these, the convolution and equivariance, do have generalizations. They look a little bit more complicated. So instead of just doing like x minus y, you need to actually apply the group operation. You're integrating on the group with respect to the Haar measure, which is nastier. But it's certainly true that if this is what your neural network implements, then ultimately your architecture is indeed going to be equivariant, even to something like permutations or rotations. So that's good. And in fact, there's a theorem, we wrote a paper about it about 3 years ago, which proves that this is all. So essentially, any kind of equivariant neural network, which is equivariant to the action of any compact group, has to implement this generalized notion of convolution corresponding to the group. Now, this is great. This is super general. It's pretty everything. The only minor problem is that it's not something that you would actually want to carry out in a computer. So integrating on a non-commutative like Lie group with respect to the Haar measure is something that you easily write down in the algebra, but actually doing it on a computer would be messy and complicated and involve all sorts of approximation errors. So the good news is that there is a more kind of principled, fundamental way of looking at this through the notions of Fourier transformation and a generalization of Fourier transformation to these groups. In particular, realizing that everything here at the end of the day is a linear action. So the way that the group acts on the inputs and these intermediate representations, it's all just linear actions of the group. That means that they're representations. Okay, so now this is another big hammer. The theory of representation theory of Lie groups or finite groups or mathematics, and there's a lot that we know about it and a lot that we can apply directly. So representation is really just a way of substituting for the group with matrices or linear operators that behave the same way, right? So I'm sure you've heard about them or you're familiar with them from quantum mechanics and so on. This is a very general concept that applies to any group. It's just a mapping, the homomorphism to these invertible maps. So And there's a lot that we know about representations. It's a very classical theory, as long as you stick to representations over the complex numbers, and as long as they're unitary. In particular, one critical thing is that these representations, no matter how big they are, like what a fancy, complicated way your internals of the neural network work, they are always reducible by an orthogonal transformation to this kind of canonical set of so-called irreducible representations. So for SO3, for example, you know what those are, you know a whole lot about them, and then you can just look at the whole picture in terms of just those. Okay. So now back to the general theory of neural networks and how to construct these layers. And you realize that in fact, this theory, once you've decomposed everything according to the irreducible representation, the theory tells you that all that you're allowed to do is take the parts of these layers that correspond to each irreducible representation and apply a linear map there, which is really just like matrix multiplication from the right by a learnable matrix. So the thing to notice here is that mathematically, this is the same as convolution. So mathematically, we haven't gained anything. On the other hand, computers are not necessarily very fond of doing convolution on Lie groups or the symmetry group with n factorial elements and so on, but they're pretty good at multiplying matrices. And so this kind of brings the whole thing down into a much more computational, much more realistic, it's actually easier to code up framework. And it's still super general, so this still applies to any compact group essentially. Okay. Now, one thing that I kind of neglected is how to do the nonlinearities. That's a little bit more complicated because I said pointwise nonlinearity, right? So that the sound, its first sight, it seems like, okay, then you need to go back to and then you need to go back to, say, SO3 and do the nonlinearity there. You have a Fourier transform that gets messy. But there are other types of nonlinearities, and in particular, again, representation theory tells you the very general thing that you can do is take tensor product of representations, and that gives rise to this Clebsch-Gordon nonlinearity, which is again very well charted. So the coefficients are known, and then nonlinearity reduces to taking the tensor product of the activations and then applying a linear transformation, which is again kind of comfortable for deep learning architectures. All right, so this was the general part. This was the general kind of prescription of how to implement the symmetries or even the conservation laws that we know exist in nature in neural networks when we're actually using neural networks to learn physics or chemistry. Okay, so this is the graphic representation. You have these learnable weights matrices, which are applied to the channels. And then you have the Clebsch-Gordon nonlinearity, and that's it. You've got an equivariant neuron. So in terms of learning forces, we tried this out in an architecture called Cormorant, and I'm going to spare you all the details. We got pretty good results at the time. This was already 2 years ago, so things have changed since then. But then this, at the time, this was pretty much state of the art with a kind of out of the box application of these principles on the QM9 data set and the MD17 data set. One thing that I just want to say here is that before going on to this, is that another nice feature of this is that because everything inside a neural network respects the underlying symmetries and follows this representation theoretic prescription, it actually looks very similar to the form of real physical laws. So that not only does it explicitly obey the symmetry principles of nature, but also everything in the neural network becomes a little bit more interpretable. And in particular, the way that particles or combinations of particles interact start looking like both the hard physical laws that we know or the empirical substitutes for that chemists use. So I think that that's important to stress that these two things go hand in hand. So understanding what you're doing and interpretability with actually reflecting the real nature of the problem. All right, so in the remaining time, I want to talk about this new stuff, which is applying this in a different round to this case of finite groups, just the symmetric group of permutations, in order to learn something from the graph of molecules. Okay, so there's been a huge amount of work on this field because graphs appear in so many different guises in learning problems. And in particular, because it's kind of a tantalizing question of how you take these intuitive and well-known and very practical concepts such as convolution, and then generalize it to this discrete structure, which locally looks very reasonable, but overall has a much less regularity than, say, the plane. Okay, so what the first question that first of all, so what are the constraints? What are the design principles for designing neural networks, convolutional type neural networks for graphs? But certainly you have this invariance issue that your graph is going to be represented as this matrix to the algorithm. But if you permute the rows and the columns, then it's still the same graph, right? So this is a spurious transformation to the action of the symmetric group that needs to be reflected in the neural network. But there are other important aspects of graphs as well. Another one, which is particularly important for chemistry applications, is that the little local features, such as individual functional groups, are really critical for the semantics, right? So the neural network really needs to pick up on these very specific, or able to pick up on these very specific local features. At the same time, okay, there's 2 minutes?
Yes.
Okay. At the same time, you, as a hint, for Frank also mentioned this concept, you want to be able to respect or able to take into account, to reflect the graph at multiple different scales. So that's for particular larger systems, that's going to be critical. And the fourth one, which is sometimes neglected, is that it's fine to call something convolution, but in specific cases, for example, when you have cycles or paths in your molecule, which happens all the time in organic chemistry, then there's a natural notion of convolution. So we know what it means to do convolution of a circle, or know it at the backbone of a molecule. And ultimately, you would really want, if that's what your graph is like, you would want your cooked up general convolution to reflect that, or to be similar to that. So this new work is about trying to bring all this together and come up with a notion of convolution on a graph which actually looks like convolution and makes sense for chemistry. So part of it is the decomposition of the graph into parts. Another part is to consider higher order activations, in contrast to the popular message passing neural networks, which always just sum. We take into account larger parts of this graph and actually care about which atom was which. So we don't impose invariance by just symmetrizing at every layer. We have an equivariant network rather than just an invariant network. But the last final component is the realization that the local graph structure, in fact, allows you to relax this equivariance constraint to equivariance to the automorphism group of the local structure rather than the full symmetric group. So that's why our architecture is called Autobahn, because it's an automorphism based neural network architecture. And the reason I'm talking about it here is because it's particularly well suited to chemistry, because you know what you want to pick up on, right? So there are these benzene rings, and you want to be equivariant to rotations around those 6 atoms. So that's exactly what we do. So we don't look at all possible permutations of those 6 atoms. We'll just look at the physically valid ones of rotations and reflection. And similarly, when we look at when we have paths or backbones of molecules, we really recover the ordering notion of convolution, while globally the whole thing is still equivariant. So Autobahn is this kind of brings together all these different features. It's globally equivariant. It does, in a reasonable way, computationally affordable way, it manages to take into account higher order activations, and it also reduces to regular convolution when you want it to. So we tried that in the Zing dataset and actually got very encouraging results. We also submitted a competition. We'll see how we do well. I think this is kind of it's a good fit for chemistry. All right, I'm going to spit the last part, despite the cute cat. Acknowledge my collaborators. Eric Tida in particular was instrumental in the Autobahn work, together with Wanda Zhu. They're both at the Flatter Institute, and my students who were involved in other parts of this work. Thank you.
Okay, thank you very much for a very nice presentation. As I said before, there are a few questions already in the chat. We will keep those for the discussion that will follow after the next talk, basically. So again, Professor Ricci, thank you very much for the presentation. Let's move on with our last presenter in this session, Bidisha Samantha from Google. And I hope I pronounced your name correctly.
Yeah.
If I didn't, don't worry, they always mix up my name anyway, so.
No problem. Yeah.
Am
I audible, right?
Yes, you are.
Yeah, okay. Thank you. Thank you very much for inviting me in this session. Let me share my screen.
Great. I think we can see your screen, yes.
Sure. Yeah. Welcome everyone to my talk. And I am Bidisha, and today I am going to talk about one of my work in my PhD. So this is called NIVI, a deep generative model for molecular graphs. This is a joint work with my collaborators from Indian Institute of Technology, Kharagpur, Department of Computer Science, Department of Chemistry, Max Planck Institute for Software System, UPF Barcelona. This work initially got accepted in AAAI 2019. A detailed version of this work got accepted in JMLR 2020. So in this work, our main contribution is to discover a sizable amount of candidate drug-like molecules using a deep generative method, which further can be given to a chemist, and that can go via preclinical and clinical development. And out of this large amount of sizable molecules, we can at last get a very little fraction of it, which is actually usable for broader use cases. So our main contribution is that to develop a model based on variational autoencoder. So NIVI or network VAE has one probabilistic encoder and a corresponding probabilistic decoder. We learn from a set of molecular graphs. The encoder tries to convert the molecular graph into a continuous latent embedding space. And from that latent embedding space, we can sample the embeddings and pass it through a probabilistic decoder, which tries to reconstruct back the original sample. But it always may not generate the exact sample. It can generate something similar to what it has seen. So it has some potential to generate plausible new candidates. So architecturally, our key innovations are the encoder is permutation invariant of the node labels, and it can be trained from variable size of graphs that can help us to learn and generalize better. And the decoder guarantees some structural and functional properties, and it can generate some structure which are valid. And also we try to extend the work so that we can generate some 3D configuration of a given molecular graph. Before I go into the details of the architecture, I will just give a brief overview of the main building block variational autoencoder. So it is an encoding and decoding module where the encoder takes any kind of an input, and instead of converting it to a fixed vector, it tries to map it to a representation distribution. By default, it could be assumed that it is a Gaussian. So we try to encode mean and a standard deviation from the input. And from there, we can sample some latent vector, which further goes through a decoder network, which is again a deep neural network. And from there, we try to reconstruct back the original input. So we generally solve or train this kind of architecture using ELBO, which has two parts. One is the reconstruction likelihood, which we want to maximize. That is, we want to reconstruct back original input. And another one is the variational loss, which tries to minimize the approximate posterior, which has been the distance between the approximate posterior, which has been learned, and a prior. So the prior, if it is not known, most of the cases, we just use it as a noise or a standard normal distribution. Now I will give the detailed overview of the encoding mechanism. So here we considered any given molecule as a molecular graph where the atoms are represented as nodes and the bonds between two atoms are edges. So our first task is to aggregate the information about the neighborhood given a node, that is to understand the local structure. So initially, every node has its own information, that is the type of atom it is, and if there is any atomic properties available. Then we start convoluting and we start aggregating the information across one-hop neighbors. Then we go on till k-hop neighbors, where k is a hyperparameter. Once we have these atomic features all in our hand, then we are also interested to understand the spatial features, that is exactly where the neighbors are situated, the 3D informations. So we actually gather in a similar way all the neighborhood locations informations. Once we have all these informations with us, our next task is to convert it to a representation space, that is to transfer them to a continuous space. And for each node, we encode a mean and a standard deviation vector. So we sample the representation per node from this encoded vector. So there are some properties which we actually achieved with this encoder architecture. First is the encoder is permutation invariance in terms of as follows. For each node U, its embedding is invariant to the permutations of the neighbored node labels, though we are accumulating the information from the neighbors, but we are using a symmetric aggregation function so that this embedding become permutation invariance. It is also permutation equivariance, that is, if we permute the node labels, their embeddings get permuted in the similar manner. And also, all the trainable weights of the encoder are independent of the number of nodes and edges. That makes this architecture flexible to be trained using different types of graphs. Once we generate the encoding, now our next task is to try to reconstruct back all this information which has been encoded in the representation space. So we basically have 4 decoding modules. First one is the node feature decoder. Then we need to decode the possible number of edges. Then where actually the edges are situated. So there is an edge decoder, and finally the type of edges, that is whether it is a single bond, double bond, or triple bond. So first we need to sample the representation. So for that, we can sample it by 2 ways. One is a conditional way, that is we can start with an initial graph, we can pass it through our encoder, get a representation distribution and sample a representation from that. Or we can start by sampling from a noise. So for that, initially we need to know how many nodes can be is possible in the graph that we estimate from our training data. And once we have these representations, we need to start decoding the node features. So each node features for our architecture, we build it as a categorical feature. And so we pass the node representation to our decoder, and that gives us back a softmax distribution. So this softmax, from this softmax distribution, we sample the node features. So next we are interested to know the total number of edges possible. For that, again, we use a decoding module and we just decode a Poisson distribution, and from there we sample the possible number of edges. Next, we try to decide that whether there exists an edge given two nodes U and V. For that, we just pass the representation for these two nodes to another decoding module, which is again a deep neural network. And it also provides us a probability that whether there exists an edge or not. Similarly, we try to decode like the edge types, that is whether it is a single bond, double bond, or triple bond. And then we sequentially decode all edges one by one. So generating a softmax distribution over all possible edges is order of V square, which is time consuming, and it is difficult to train a neural network like that. So we do a negative sampling to reduce it to order of E. Finally, when we have all these node connectivity decoded, we are also interested to predict that what could be a feasible 3D configuration of it. And for a given node, its location is dependent on the neighborhood location. So we first gather the information for the neighbors again, and then we try to pass it through another deep neural network which tries to decode a multivariate Gaussian, and from there we sample the 3D coordinate. Now, given the connectivity, we can sample multiple 3D configurations, many of them which may not be correct. So we just use a software called Gaussian to estimate the potential energy for each of these configurations, and we report the structure with the minimum energy. To train this architecture, we use the regular VAE objective, which is ELPO, that has a reconstruction likelihood as well as variational loss. Now, this calculation of reconstruction likelihood actually is a function of the edge sequence, how we are considering the edges. Given a graph, there can be multiple of such edge sequence. To make the training permutation invariant, we sample multiple times different nodes, and we do a BFS starting from that node and consider the discovered edge sequence to estimate the likelihood, and we aggregate this value. For our experiment, we have used Zinc and QM9 dataset. And for each dataset, we have selected a subset of samples where we considered only the molecules which are having carbon, hydrogen, nitrogen, and oxygen as nodes, and only single bond and double bond and triple bond. And for the graph, we consider nodes as an atom and edges are bonds. And this is one of the initial results, where the center highlighted one is a sample from the training from Zinc dataset. Once training is done, we pass it through our encoder to generate the representation distribution, and we sample different representation from this distribution and try to decode back the original one. And as you can see that the decoded ones are structurally similar to the center one, but they are not exactly same, which shows the potential that we can generate similar looking plausible molecular structure. To quantitatively report the performance, we use three metrics. One is validity, next one is novelty, and finally uniqueness. Validity is measured by the chemoinformatic tool RDKit, where we pass the structure, and it does some basic computations like whether the valencies are met, if it is an aromatic, then whether kekulization can happen, etc. And if that passes the basic checks, then it says it is a valid one. But whichever is been identified as valid may not be a synthesizable molecule. And novelty, we just simply check that whether the generated samples are present in the training or not. For uniqueness, we just measure that how many of them are unique. And we compare the performance with several state-of-the-art methods. So those are categorized by two different categories. One is graph-based, which considers molecules as molecular graph like our method. And the other one, they consider molecules, one string representation of a molecule called SMILE string. And one can see that the text-based methods, in terms of validity, their performance are underwhelming.
Ding.
Yeah. In terms of novelty, we can see that all of them are kind of equivalent performance. And in terms of uniqueness, there are two methods which are similar to our performance. Now I will move to the next part where we are not only interested to generate some valid structure, but also a structure with certain property of interest. For that, we develop a decoder architecturally similar to the original one. And whichever we have knowledge we gather from training the first model, we just copy those parameters so that the new decoder can benefit from the inductive training of the original decoder. Then we train the decoder using KL control, which is this loss function having two terms. The first one penalizes low values of the molecular property of interest. So we want to be very aggressive about generating some structure where desired property should be very high. And the second part actually penalizes structural dissimilarity with the original decoder. That means we want to generate some structure similar to the training molecules. And there is this parameter rho, which actually tries to keep a trade-off between these two. And we can see that when this rho value is very low, that is, we are very aggressive on generating some structure whose property value should be high, we are able to generate like some molecular structure whose log p value is very high, as well as QED value is very high. However, further inspection reveals that as you go from left to right, where rho value is increasing, then we can generate some structure which are looking similar to the training molecules, and it could be more synthesizable. Whereas when we make rho very small, even though we are generating some structures that may not be that stable or valid. So we use this approach to further make some or generate some stable structures. So here in the left and the right, the connectivity is constant. The number of atoms, everything is constant. It's just the 3D configuration is different. So we train our model such that it can generate some 3D configuration whose single point energy should be very low. That means it should become stable. And we can see that there is a transition, and we can generate some stable structure. With this, I will conclude my talk. So we have introduced a variational autoencoder for molecular graph, and that was that time beating the state-of-the-art approaches. And we also tried to investigate like whether this could be used for dynamic graphs that may allow us to simulate chemical synthesis, or whether we can extend this generative model which can learn some candidate with just the desirable property, not a high desirable value. If we just provide an exact value, whether it can generate a structure with that. So with this, I will conclude my talk. Thank you very much.
Yeah. Okay, thank you very much. So thanks to all three presenters for the great talks. So at this time, we're going to start the panel session. And for those of you in the audience, if you have questions, please enter your questions into the Q&A feature of Zoom, and I will be trying to keep an eye on those and take some of those. So let me start with kind of a general question, I guess. So, I noticed that all of the methods that were discussed in this talk, these are all deep learning methods. So I'm wondering, basically, what your thoughts are on shallow methods in this area. So, we could have something like a structured kernel method to solve some of these problems. Are shallow methods dead at this point, or where do you think that these methods might be applied?
I think we're hoping that we're not dead, because we ourselves worked on some of them, which you might now call shallow. At the time we called them things like kernel methods. If this problem is simple enough and you have a decent chance of creating a suitable basis set for the function that you're trying to learn, then actually something like a kernel method is still a reasonable thing to do. And like some of the experiments certainly that I presented, just related to learning these properties of molecules as computed by DFT. A DFT itself is an approximation to the actual solution to Schrödinger's equation, and sometimes a bit of a rough approximation. And experience shows that if, depending on the downstream, depending on what you're learning, where the data comes from and what the downstream application is, for example, molecular dynamics, then a shallow method in some cases is still perfectly competitive.
I mean, if you know your features, then everything is shallow, right? Then you need one layer only. The problem is often you do not. And also, I mean, as I tried to allude on the last slide, deep learning is more than just depth. It's more than just like having a number of transformations to your problem. It's more, I'm thinking more of it like a sort of a programming language that, or it's kind of, is in a way, it's kind of the next level of algebra, doing algebra, right? It allows you to do algebra not only forward, but also backward in a way that you can tune any sort of parameters in a way. It's not just about the number of layers. It's the combination of having many layers, of having differentiable layers, having backpropagation, and a learning algorithm that uses it, right? And that together gives you a package that allows you to automate computations that you can do forward and backward in a way with which you can do parameters. And that's a very powerful package. And it allows you to develop and be very creative and do very complicated things. Whereas with a shallow learning algorithm, that can be perfectly fine in specialized cases. But it's more like one module. It's like you have this input and this output, and if a shallow learning algorithm is fine for that, you can just plug that in. Whereas like deep learning is more like an ecosystem.
Maybe another thing to add is that deep learning is a good fit and performs well when the problem itself, or the data that you're learning from itself, has this kind of hierarchical structure, a bit like the multi-scale thing that I mentioned, I alluded to. Also in the case of classical convolutional neural networks for images, there's good reason to believe that there is this hierarchy of like smaller features being combined into larger features and so on and so on. Similarly, if you care enough about your molecular system, then you can come up with this multi-scale view of it in terms of individual atoms and functional groups and so on and so on. So if you want to build a learning algorithm which reflects this structure, then actually a deep neural network is very natural, because it automatically starts looking like that. So you can encode these complicated hierarchies easily and then just send the derivatives through. But as Frank just said. I mean, if your system is small enough, if you only want like the force from a couple of neighbors, then maybe you don't need a full hierarchy and so on, and the linear method is just fine.
And presumably the amount of data matters too. I mean, if you don't have enough data, then you're going to be fitting a huge number of parameters to a model that is going to overfit.
Sure.
Okay, so I have a question also for Badisha, and also somewhat to Risi as well. So when I was watching your VAE presentation, I wonder if it's possible to think about an encoder that uses the kind of structure that Risi was talking about in his talk, that explicitly builds in certain equivariances. Do you have any thoughts about that?
So I think, yeah, so the current structure, as I was saying in my talk, it is the encoder, from the encoder perspective, it is permutation invariance as well as permutation equivariance. So because the trainable parameters, etc., I mean, the architecture was built in such a way that if you permute the node labels, so currently it is informed, so the input for our model is just a graph, a molecular graph. So it's just the nodes and the edges. So if you permute the node labels, their embeddings also get permuted in the same manner. So in that point, we can say that the current encoder is still permutation equivariance, as well as it is permutation invariance because we aggregate the information in a way that the aggregation function is also symmetric. So yeah, but like I was following Rishi's talk, so in order to achieve that, we probably need to provide certain constraint in the architecture level in order to achieve.
That's actually a great question. Because I have a very clear answer. So we tried that. So sometimes the backstory behind the paper is as informative as the paper itself. So for years, we've been dying to say that it makes sense to worry about higher order equivariance, in particular in this graph learning problem of learning from molecules. Because there's a nice mathematical theory behind it. So if you really care, then you can express everything in terms of irreducible representations, the symmetric group, and everything fits together perfectly, right? It just gets a little bit complicated. And then the question is, like, how much do you really need this for your specific task? And are you willing to put up with the added computational expense? So what I'm talking about in particular is these equivariance to not just the first order permutations of the vertices, which corresponds to, this vertex goes here, that goes, but second and higher order permutations, which means that, or second and higher order equivariance, which means that the internals of your neural network reflect not just what happens to individual vertices, but care about what happens to pairs and triples and quadruples and so on. And we thought that, okay, a generative model is the ideal way to demonstrate that, because there you really, because if it's just an encoder, then maybe these message passing tricks are good enough. But then the story just gets more complicated, right? In particular, if you want to have a higher order equivariant generative model, then the latent distribution also needs to be second or third or fourth order equivariant with respect to permutations. And that's a whole different story. So like this is changeable distributions over permutations, but in the infinite case, the story is simple. There's a generalization of the affinities theorem. in the case of just finite number of things that you're computing, actually, there is a interesting but non-trivial theory behind it. Diaconis and Friedman wrote the classical paper in the 80s. So that really complicates things. And we're stuck in this situation where we wanted something that is higher order equivariant, and we're looking at molecules, and we really wanted something that is equivariant the right way for organic compounds in particular, where you care about not so much individual atoms or pairs or triples, but you really want those benzene rings. So you want 6th order equivariant. And 6 is a little bit too high, because then you need 6th order tensors. And that's like from a computational point of view, that's nonsense, right? So it's purely in the land of fiction. It's great in math, but in practice, nobody would use it. And so the story changed last year, because Eric, who is the main driver of this project, was looking at this problem all year and tried various things. And then we realized that actually the graph itself gives a huge clue. So if you really have these cycles and paths, then you don't need to, the key insight was that you do not need to be equivariant to the full symmetric group. You just need to be equivariant to the symmetries of the local structure, i.e. the cycle, and then you really can be 6th order equivariant. So that is what brought down this mathematical theory to something which actually is implementable, this local automorphism idea. So now it's not just fiction that we can have these higher order equivariant architectures, and it would be really exciting. I mean, we're working on this, but it's not trivial, of making a generative model out of this. So this is a great question, because it's exactly what we, and I'm sure many other people would like to do, but it's just a little bit more complicated.
I see. Very interesting. Thank you. Okay. Okay. So Frank. So let's see. I have a question here. How does the deep learning approach overcome the Fermion sign problem associated with traditional stochastic QMC approaches? Coefficients of the different determinants are in general complex, and accumulating phases must still be a problem.
So everything here can be done in real space, first of all. So we are dealing with molecules. It's not periodic systems, and it's not the time-dependent Schrödinger equations, just the stationary Schrödinger equations. So you can always get away with real-valued wave functions. And everything can be done in real space. If you had any complex valued wave function, you could just find a complex coefficient so as to make it real, and still an eigenvalue. It's still a solution to the eigenvalue problem. How does it overcome the sign problem? Of course, you cannot fundamentally overcome it, right? So in general, you can always find a problem that is sufficiently complex that you will need exponential time for the solution. We've not fundamentally changed it, but the practical issue with the sign problem occurs when you use, for example, diffusion Monte Carlo, where you want to decide where is the region where your wave function crosses changes sign, so that you can run your walkers inside this zone. And then the difficulty becomes defining that zone. And of course, that zone is like in a 3n, there is a 3n minus 1 dimensional hyperplane, and it's very convoluted. So it's probably very hard to find. And the trick here is that basically you're not using diffusion Monte Carlo, you're using variational Monte Carlo, and you're using deep learning in order to find this function. So you can actually search the boundary, if you like. That's a way to say it. So we're not fixing the boundary as it's done in classical quantum Monte Carlo, where you usually do like a Hartree-Fock or a Cas-STF calculation, and you fix the determinants, and then you just vary something, which is usually just a symmetric function multiplied with this antisymmetric part. But we're really varying the argument of the antisymmetric part. So in a way, we're replacing the search over exponentially many determinants which is NP hard, with a search over exponentially many continuous functions. And it's not mathematically clear if that's a good idea or not, but that's something that deep learning is good at. So that's the idea.
Cool. Thank you. Okay. And someone else asked, is the idea in the Schrödinger model that you were discussing, is the idea that you're adding the Schrödinger equation into the loss function?
Yes. So basically, the loss function is satisfied when we have found an eigenvalue of the Schrödinger equation, and specifically, if you look for the ground state, just the lowest lying eigenvalue. So the variational formulation, so minimization of this energy, is just a different way to formulate the eigenvalue equation. So it's really the loss function is encouraging to solve the time stationary Schrödinger equation in this case. And that's what I mean by the physics tells you what the loss function is in some of these cases.
Good, thanks. Okay, let's see here. This is for Risi. You mentioned there's data loss through invariant layers. Is that is the lost part of the data useful if it doesn't follow the laws of physics?
So in order to follow the laws of physics, what you need is your network as a whole to be invariant, not the individual terms to be invariant, or not the individual layers to be invariant. So the idea behind equivariance is that you do not symmetrize over everything in every layer. You just build a neural network where all the quantities transform in a controlled manner so that you can symmetrize at the end. So these two things of losing data through symmetrization is not at all a necessary side effect of respecting the laws of physics. And in fact, there's a very simple way of seeing this. Just take any equation of physics, like what do they look like? And there are certain equations which, like in thermodynamics, which only involve scalars, but most equations involve vectors and tensors and so on. Those are really just equivariant quantities. And usually what happens is that you have an equation with terms involving vectors and tensors of different ranks, and they combine in specific ways. And finally, when you evaluate the whole expression on one side of the equation, then you get a scalar, right? Energy equals something. But just because energy is a scalar, it doesn't mean that everything else that is in the equation is also a scalar. So this is the same situation with neural networks, that internally you don't want everything to be invariant. It's much more natural to expect everything to be equivariant. Now, having said that, my comment came up specifically in the context of these graph neural networks. And by far the most common type of graph neural network currently are these message passing neural networks, which do symmetrize at every single aggregation layer. And they work in many cases, they work surprisingly well. So, so it seems like for many tasks, that's fine. But you need to be aware that because if the aggregation function is symmetric, it's something like a summation, then you have the potential of losing information, right? So you forget which atom was which as soon as you do that. And ultimately, is that a problem or is that not a problem? Ultimately, I think the only way to know that is to try out both, try out this more fancier higher order equivariant architecture and see whether it does better.
Okay, thank you. Okay, so and let's see, Frank, question for you. So when you were talking about your generative model, you had this Boltzmann generator. It looked a little bit like a GAN in a way, but not a GAN. So how are these things similar at all, or not at all?
Not really. So the basic idea of directed generative models, such as GANs, variational autoencoders, and these normalizing flows, is all that we start with a random variable from a simple distribution, such as multivariate Gaussian, and then transform it through the network to something interesting. Right. So in that sense, they're all the same. But the fundamental difference between these three is they're kind of on opposite ends of the spectrum with what respect you can actually compute. So with a normalizing flow, and the Boltzmann generator uses normalizing flow, because it's an invertible structure, it allows you to compute the probability of generating the output. It's also called exact likelihood model, because you can compute the exact likelihood of generating something from the model. And this allows us to compare the probability of generating these samples with the probability density they should have in the Boltzmann ensemble or in any other ensemble, right? Because up to the prefactor, we know that. So we know it's e to the minus of some energy, and we know the energy. We can evaluate for every x. And that's key in this method. That allows us to train it to generate something similar as the target ensemble we want. With a GAN, we have absolutely no idea what the likelihood is. So it only works on data. We can just train it to do similar things as examples that we show it. The advantage of it, of course, it doesn't have to be invertible. It's just a feed-forward network, and it just allows us to have more flexibility with the architecture. And that's why it can be much more powerful, generating beautiful images, for example. But it wouldn't allow us to solve this problem.
Cool. Thank you. Okay, so let me ask you all. This is a question for everyone. It's kind of a higher level, slightly less technical question. You know, in the Freie Institute FRP, we've been working on building collaborations between machine learning people and people from chemistry and materials science. And one of the challenges that we run into is, you know, allowing people to actually kind of work together when they come from completely different backgrounds. So, you know, I come from a machine learning background and don't come from a, say, chemistry background. So, you know, and it sounds like in your cases, you come from more, say, a machine learning background, perhaps. So how do you successfully work with people in the fields that you're working on in these applications?
Yeah, I can answer, like I can speak for like my case. So my work is like a collaboration between Department of Computer Science as well as Department of Chemistry. And both of these departments are like having a totally different background. So what I initially faced is that there was a lot of gap in understanding like the overall problem. And I think that is because we who are coming from a machine learning background, they only knows like machine learning in depth, and people like coming from a chemistry background, they know like more chemistry in depth. So it is, I think it's very important to first understand the problem in an abstract level such that both of these parties can grow the interest. For our case, it's like the problem, we started it from a machine learning perspective, and then that application actually we got interested with, and then we reached out to the people of chemistry, but they were sort of in a mode of denial that it is at all possible to achieve using machine learning. So because they had like sort of these reservations, and they have like their methodologies which work well for their cases. So what gradually we developed is that to understand and to explain them the abstract level what we are trying to solve, and then sort of find out like where the interest matches, and from their start of showing them some initial results, build their interest, and then getting their input was also very important for us. For example, when we tried to move from graph towards a 3D configuration generation, that time it was a very interesting collaboration. But before that, it was initially very difficult to build that and bridge that gap.
Yeah, one thing that I find is that it's important to build long-term collaborations, because otherwise simply individual research groups' interests or the way their field works can result in a situation where the kind of objective functions are different on the two sides. So if on the machine learning side, the objective function is to just get one NeurIPS paper in and have an experiment which is good enough to make the NeurIPS paper fly, but doesn't reflect actual interest in the underlying physics or chemistry, then that's not very satisfactory for the science partner. But conversely, if the partner on the science side is just focused on getting a specific paper out by kind of any means, and that can easily mean just playing around with some existing architecture until you get decent results, then that's not very exciting or rewarding for the person working on the machine learning side. So I'm hoping that, as it is now clear that machine learning is going to be an integral part of the scientific discovery process, that it's not this kind of strangeness between the two cultures is going to go away, and there are really going to be like long-term collaborations where both parties start to understand each other's viewpoint.
Yeah. So I have a very strange background, and it's probably not a good recipe for reproduction. So I have a bachelor in engineering, a master in computer science, and a PhD in physics. And now I'm in a math department, and most of my co-workers are physicists. So don't copy that. It's just like that. So it helps to have kind of a bit of an interdisciplinary background and interdisciplinary co-workers. That's very important. If you're asking like what are the ingredients to be successful in this field, I would say there are three. It's genuine interest for physical principles. I think you have to know some physics basics, even if you're coming from the machine learning side, to kind of understand the basics, and that's quite a lot of work if you haven't studied that. But I think that's important. And the second is you have to be pretty good at software and programming, because basically building any of these systems is still quite engineering. So you really have to build a lot. And the third is be good at math, at least at the basics, like be really, you should be able to write like matrix vector equations and matrix decompositions while sleeping, basically. And I think if you can do these three things, I think then you're pretty good. Then you can go in any direction you want. So that's kind of my sort of advice.
Good, thank you very much. Okay, so let's see, how are we doing on time? It's 2:48. I think we are just about out of time. So maybe that's a good question actually to wrap up on. Thank you again, Frank, Risi, Badisha, for your participation. Thanks again for the audience, for the questions.